Alrighty, so this is the help on homework assignment number 13, states of matter. So my goal here for this one, same as before, is I want to kind of go over the problem a little bit, just like read it, and then give you some time. You can pause the video in class and then work on it, see how it goes. And then once everyone's kind of ready, then play it and go through the answers and make sure you got it right. So looking at the paper here, the first two problems are heating curve problems. And number one says substance X has the following properties. Sketch a heating curve for substance X and calculate the total heat energy Q in kilojoules needed to convert 35 grams of the substance from -20 to 90 degrees Celsius. And I'm just double checking. It looks like everything in the box is in Celsius, 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 Celsius. So we're good to go. We don't need to worry about any temperature conversions and stuff like that. And let's see. It says that our boiling point and melting point are at 80 and -10. So at 80 and -10, when you're drawing your little diagonal over diagonal over diagonal, make sure that your flat portions are there at -10 and at 80. So I'll just do that really quick. Got a ruler. Doesn't really matter where they go. We should make sure we have a flat portion here and a flat portion here-ish, something like that. So those are the melting and boiling points. And then just connect it. So we're going from -20. So we need to draw this down to -20. -20 up over, oof, this one's gonna be real steep. I didn't really think that through. Whip, 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 over, and then up to 90. So just a little bit further. Whoop, maybe like that. Doesn't have to be like mine, as long as it's got some diagonals and looks generally like this shape, it'll be good. Don't worry too much if you have the same slopes as me. All right, pause this video now, and using this graph that we made, figure out how much it would be from 35 grams of this substance to go from there to there. All right, so here's where I started. I know that on the diagonal sections, I'm going to be using Q equals MC delta T, Q equals MC delta T, blah, blah, blah. I just have to keep track of the temperature ranges for each one, and also which C I'm using, because in section A, I just labeled them. In this section A here, this is where the solids exist. So I need to make sure that I use CS for solid in section A. In what I called section C, this is where liquids live. So I need to make sure that this is Cl and up here Cg. Similarly, for section B, I need to make sure that for delta H, this is where I put the fusion for melting. And for evaporation, I need to use delta H vaporization. So those are my formulas. And then just running through, I'll do one of them. The mass is 35 grams. CS is 3.0 joules per gram Celsius. And the temperature change is from -10 minus -20, aka 10 degrees. (1050 joules). So that's the answer for my first section. That's how much energy to get from there whoop, to there. Okay, I'm not going to help you with the rest of these because you should be able to plug these values into the equations, into the calculator, but I will give you the final answer so that you know if you're doing this right. Let's see, so for this one, and email me if this isn't looking right, but when I did the math, I got that my total was 18,025 joules. And then when I converted to kilojoules, it was just 18. For this one, I got, I think, 7,000 joules. And this one was final answer 1750 joules. 7875 joules, and I think 350. So double check me, but that's what I did for this section. Show your work, of course. So pause the video if you need to finish those up. Then down here, the next one is also a heating curve. It looks like it's probably the heating curve, yep, of water, because it's going to be boiling at 100 and melting at 0. So let me get my lines in here. So we're melting at 0 and boiling at, that looks like it cut off, but that says 100. We're starting at -15. Who knows where that is because it's not on my graph, but we'll add it. -15 down there. Boop. And we'll be heating it up to, oh, we don't know. We don't know how far this heats up. I mean, like, obviously these lines go on for forever, but we don't even know where to stop it at because it says that we start at -15, then 3 kilojoules of energy goes into the system. What is the final sample? Like, we don't even know where it stops. It's just energy in, and it's like, where does it stop? We don't know. So we have to figure that out. That's kind of tricky. Also, this looks a little bit tricky too, because we have to pay attention to the fact that this is in joules and this is in kilojoules. Also, this is in grams, which makes sense for here, but how are we going to do this where it's kilojoules per mole? Okay, so let's call this section A, B, C, D, E, just for clarity. And pause here and see if you can figure out how much energy it takes for section A. Once you figure that out, Do you have enough energy to keep going? Because if so, see if you can figure out section B, etc., etc. So maybe take, I don't know, 5 or 6 minutes and see how this goes. So pause the video. Okay, so hopefully you paused the video and worked on this. Section A is a diagonal portion, and the formula for those is MC delta T. So M is the mass. It's telling me that I have 5 grams. C of the solid section down here, CS, is 2.10 joules per gram Celsius, which is good because that will get my grams and grams to cancel. And my change in temperature is from 0 to negative 15, 0 minus 15. That gets rid of Celsius. So my Q of section A here appears to be 157.5 joules. That's how much energy to get just the first diagonal bit. 3 kilojoules of energy went in to the sample, and 3 kilojoules is the same as 3,000 regular joules. So 3,000 joules are getting pumped in, and going up section A required 157.5 of them. Oh, we still got plenty. We can keep going. So let's see how much section B would cost us. Section B is a flat component. The formula is M times delta H. Oof, here's the tricky thing though. That delta H, it's for melting. I want to use the delta H fuss, but kind of weird. Check this out. It's in kilojoules per mole, but I only know how much this is in grams. So I need to first do a grams to mole conversion. So I have, let's see. I'm gonna do this in a different color so it doesn't get mixed in. I have 5 grams of water, or technically ice, but still H2O. And water is 18 grams for 1 mole. So by doing this, I'm now into moles. And now I can plug in that it's 6.01 kilojoules per mole for my delta H. And let's get rid of kilojoules and just see how many joules this is going to cost. $1,669. And this is for QB that I apparently did in green. All right, so that's QA and QB. The total amount that went in was 3,000. So I'm pretty sure we still have some left over. 1669 plus 157.5. We're only up to 1826 out of the 3,000. So we've made it past section A. Yep. Boop. Made it past section B. Boop. Something tells me that with our remaining energy left, we're not going to make it all the way up part C, but that's just what I think. So let's figure out how much we have left, because we've used up this amount, and there was 3,000 joules going into the equation. So after making it to part B, we will have 1,173 joules left to use. We got to see how far up part C we can go with just this 1,173 joules that are left. So however long we make it up QC, that's what this equals. So I'm going to do this a little bit differently. QC, since it's a diagonal bit, the formula will be MC delta T, and of course we need the liquid amount. The mass was 5 grams. Cl is 4.18 joules per gram Celsius. And we don't know the change in temperature because we don't know how far up this we're going to get. We do know we're starting at 0, but we don't know how far up we're going to get. So let's say we make it to, gosh, I don't know, probably halfway. We'll say this is X. We don't exactly know where X is, but it's somewhere. And we're going to make it to X minus 0 degrees Celsius. X up top, 0 on bottom. And we know that we only have 1,173 joules of energy. So in this case, I'm solving for X to see how far I make it up. And it looks like X equals 56 degrees, just kind of almost where I had it. I had it at 50, but maybe 56. That's as far as we can make it on this energy that we had left. So the questions were, what is the final temperature of this sample? 56 degrees. What is the final phase? We made it to the liquid phase.